Hello guys, we're back. Sorry about that. We had a couple of issues here in the studio, but we are here now, and we're going to be talking about robots, which is our favorite thing. So once again, we'll introduce ourselves. My name is Jose Avendano, and I'm a robotics technical evangelist here at the MathWorks. And with me today to talk about robots and ROS, the robot operating system, is Ronal.
Hey everyone. Thank you for joining us today. My name is Ronal George. I'm an application engineer based out of Natick, Massachusetts. I primarily work on robotics and autonomous systems, so products such as UAV, navigation, ROS, and robotic system are my core focus. Now, today we'll be showcasing some things that we can do with MATLAB when connecting to ROS networks. If you're starting to work with a ROS-enabled robot like this, it makes it really easy to first bring in some sensor data, maybe run some actuator commands to see how that robot operates. And of course, finally, we can also deploy nodes that were built directly from MATLAB and Simulink.
That sounds great. Ronald, it looks like we're going to be working with something that looks like an RC car. Would you mind telling us a little bit more about what this robot looks like and what it has on it?
Yeah, sure. Before I get to the robot itself, let me talk about what we wanted to do when we got this robot. So our goal when we got this robot was like, hey, we need to navigate this robot from one office to the other office. Now, as you can imagine, this includes things like mapping the environment, creating a plan to go from one end to the other, actually controlling the robot while it goes through there, and maybe some autonomous scripts, such as what do you do if someone walks in front of you? How do you avoid that? So that's kind of what we started out when we got this robot. And as you can see right now, we were able to take the robot from my office, which is at one corner of our office building, to one of my coworkers' office, just navigating it autonomously. So we told it, hey, get to the other end, and it's got to figure out how to get there. So that's what we're going to build through. Of course, during the entire prototyping stage, we used ROS. We used ROS to bring in data. We used ROS to send actuator commands. And then finally, as you see it run on the hardware that was completely deployed as a ROS node directly from MATLAB and Simulink. All right, so let's take a look at what this robot actually has. This is a really fun piece of hardware. You can see that it has a Z camera. It's actually a depth camera, so it has both RGB and depth images. It actually comes with a little odometry, VIO, visual inertial odometry sensor on it, so it even gives you pose information. A couple other things that a car like this is going to need: a battery, so you can actually run it. This actually has a NVIDIA TX2, which is a really powerful embedded platform to run Linux, run a bunch of your ROS nodes that you've built. The chassis, there's a motor controller. There's a SparkFun 9DOF IMU, they call it 9DOF, 3-axis in each of axle, mag, and gyro. And then, of course, a rangefinder. So this is a 270-degree Hokuyo rangefinder. That's how we can do some localization, make sure if there's any obstacle in front of us, navigate around it, and things of that nature. Awesome. So just to jump right in, let's look at how MATLAB can interface with ROS, how MATLAB can connect to external ROS networks, or even just simulated ROS networks. So there's 3 ways we support working with ROS networks. One is the standard, you've recorded a ROS bag, just a bunch of sensor information that you want to play back to build out some algorithms. That's like a very seamless way to play back some data that you've already recorded. The second one and the third one we'll be looking at today, which is desktop prototyping. That's connecting live to your ROS network and bringing in data and sending out data. And then finally, we'll also take a look at deploying nodes. So be it a MATLAB function or a Simulink model, we can generate ROS C++ nodes from that and then move it over and build it. There are even ways where we can move this over and build it directly from Simulink. Cool.
Yeah, Ronald, one quick question. So
yeah.
I see in there that you can use simulators as well. So obviously not a lot of people are going to have this exact car with them or access to it. So can you tell us a little bit more about how they can explore ROS and using MATLAB with some of the simulators?
Yeah, actually you bring up a really good point. Before you start working with hardware, I would highly recommend going into a simulation environment. Why? Well, one, first you have to get the hardware actually running to be able to do anything. That's going to take a long period of time. Second, whenever you want to test something with hardware, your battery should be charged. and you should have network communications, like you should have Wi-Fi or some way of connecting. All these are just going to be blockades to actually getting what you want done. So I would recommend starting with simulation environment where your experiment is repeatable. You don't have to. You can run one command and reset the robot to the original place rather than running around grabbing it and coming back and placing
there's a
it.
sense of safety too, right? Because your robot
Absolutely.
can take off and just like crash into something.
Right. So you want to do some work in the simulation environment. Just verify your algorithms, verify that you're getting the right sensor data before you move on to hardware.
Great.
And that way you also have something to compare to see what the hardware is actually giving you and why that data is coming through.
Sounds good.
Awesome. So let's jump right in. Now, you can see that I have MATLAB on my right side, and I have a Linux environment on my left side. So to start off, I want to talk about just this. Today, we're going to work with ROS1, which means I have to set up the ROS IP and the master URI. And that's what I'm going to do first. So this is a very simple script. You can see I have one for hardware and one for my virtual machine. I'll go ahead into my virtual machine and just make sure that I have my ROS IP and my master URI set up to what I need it to be. Now, if you're ever facing any communication issues between your master and maybe an external node, this is probably one of the reasons that's actually happening. So you can see I've already set up my VM to have the right ROS master URI, and its IP is going to be the same because that's going to be my master. So with that, let me actually go into my workspace, which is my Catkin workspace. Here, if you've worked with ROS before, you know why you have to source devel, and it's going to give this terminal access to where my ROS operating system is, maybe any other additional dependencies that I need. Sort of like initializing your MATLAB path.
Right. And if you guys are new to this, we have a lot of tutorials in our documentation for the ROS toolbox, which will help you walk through how to find this IP address, how to get this started. So make sure to check that out after. Right.
So the first thing I'm going to do today is launch an environment that kind of represents a home. This is a model environment that's provided by AWS. It's called AWS Home. So as soon as that launches, you will see what we have in there. I'll minimize this for now. So here I'm opening up Gazebo. It's a very common simulator for a lot of people working with ROS. Other than ROS, we have other interfaces to work with Gazebo too. So if you're not working with ROS but still want to actuate something in Gazebo, we can absolutely support that. So here you can see it's a really nice environment. It's got a living room, a bedroom, a lot of different assets such as couches, a barbell if you want, and a couple other things that we've put in the environment. Now you can see that I have a robot here. It's a mock robot that I built, which is very similar to the frames of this robot. So it has the LiDAR at the right place. It has the camera at the right place. It uses an Ackerman or a car-like steering model. So the front wheels will steer and the back wheels will provide acceleration of torque. All right, so once you have this enabled, the first thing we want to do is make sure MATLAB is also aware of what your master's URI is and what MATLAB's own ROS IP. So let's go ahead and start bringing in some data. Now that I've set my master and my ROS IP, I can just go ahead and run ROS init. That's actually the command that's going to launch MATLAB's ROS network. It's going to connect to the master. If a master doesn't exist, it's going to create its own master. So MATLAB can be the master that you connect to if you need. So you can see that I have my ROS master URI, my IP, and I've connected as a global node, which means if I go into my actual master and just take a quick look at what nodes are available. Oh. Oh, I'm in Catkin workspace.
There we go.
Right, so you can see here, you can see that MATLAB is attached as a node.
OK, great. And we also noticed there that you have a lot of nodes going on. So
Right.
Clearly, this is a pretty complex robot.
Right.
So you want to tell us a little bit more about all the nodes
Sure.
that are going on there?
Yeah, so this robot actually comes with a package that lets you have different levels of control over it. So if you see that you have, say you have an actual RC controller or a controller in your hand, plus you have an autonomous script, maybe sometimes you want to take over. Maybe the autonomous script is navigating in a way you don't want to go, so you can have a prioritized RC controller that you can override autonomous commands. So that's available there. There's an individual node for the camera. There's an individual node for the LiDAR. There's an individual node for the actual actuation of these. That's why we have most of these. And you can also see we have a list of topics. Now, if you guys are not aware, topics is a way for you to communicate. It's almost like a channel of data that comes through. There are standardized formats, so camera data will have the RGB signals. LiDAR data will have ranges and intensities. It's kind of a standardized way for realizing or bringing in sensor data or sending out actuation data. And you can see we have a large list of topics here.
OK. We'll take a quick break there. We have a question from the chat. Somebody asked, if you had to recommend a path on how to learn ROS, and I'm familiar with MATLAB, how would you go about it?
That's a really good question. We actually have a couple nice tutorials that go over like getting started with ROS, connecting to ROS, deploying some code onto ROS. I would recommend starting with those videos. Those are a really nice way to start. And with ROS, I think it's important to get some hands-on experience. You can read a lot, but until you actually get into it, you're not going to grasp most of the pieces. So do what I'm doing here. You can open up, if you've had MATLAB, you should also have access to this virtual machine that we provide. It comes with all the packages installed, so you can launch one of our examples and get started with like moving a robot around, bringing in some sensor data from that robot. And that's going to give you an idea of how to work with ROS.
Yeah, and we have, like Ronal said, we have shared files in the past. So if you go and look up for our robotics arena tutorials, you'll see videos, you'll see files that accompany them. And one of the hardest things about ROS is setting up an environment, because you have to set up a Linux environment and add all the necessary libraries to it. We already provide a virtual machine with an environment ready to go, where you can just open up things like Ronal's doing right now. You can download that from the MathWorks website. It goes with the documentation, and then you'll be able to start playing with robots immediately. So highly recommend to check that out.
Completely agree. Awesome. So we've already connected to our virtual environment. We can see what nodes are running on it. A couple standard ROS commands. You can query the type of a topic, so it's going to tell you this is a laser scan. You can query information about a topic, so it tells you what type it is, who are publishing that, and who's subscribing to it. Good way to know like where this data is actually being received. So let's move away and actually talk about subscribers. If you guys are not aware, subscription is the way to receive some data. In MATLAB, we have to initialize a subscriber, as I've done here. You can see on line 11, I've initialized a laser sub that subscribes to the scan topic. Now, after that, I receive that scan topic, and then I plot it. Now, if I run that, you'll see as soon as I initialize that, it tells me everything about that topic. And if I scroll further down, you see this kind of maze-like environment, which if I scroll out and look here, you'll notice that it kind of outlines exactly what my robot is, the LiDAR on my robot is seeing. So it's that easy. You generate a subscriber, and then you can go ahead and query what that's reading. This could be a LiDAR. This could be camera information. This could be multiple other sensors, like just torque sensors or force sensors, if you'd like. All right, so you can do something else, too. Because we're working in Gazebo, let me actually just move this little guy further up, right? So I've reset kind of the position of this robot. And what we can do in Gazebo with ROS is we can use something called as services. These services are sometimes launched directly with Gazebo. And services are slightly different from subscriptions or publishers. A service is going to do an action that you've pre-decided. So here, this service is just going to reset my scene. So once I enter that, you can see that the whole world was reset. This is another reason simulation's much better to start with. If you were testing something and it went and crashed into something, you just reset.
We didn't have to get up, and
I
the
didn't
robot
move
just
a muscle.
moved from one side of the room to another. Which
Right.
is great, right?
Right, so there's two things, services and actions. We're not going to get into them today, but it's just other ways for you to do some back-end processes. Right, so let's actually talk about publishers. So we talked about subscribers. That's when you can query data, bring in data. A publisher, as you can imagine, is something that's going to send out data. So here I have a topic that's a navigation topic that goes to the actual robot in there. You can see that I've created a message. As soon as you create a publisher, you can just use the ROS message command and put in a publisher or a subscriber there. It's going to create a message structure that's relevant to that publisher or subscriber. So once I've done that, I can go and modify. So let me actually just show you these. Once I run that, you can see that, well, message contains data about what type of messages, it contains a header, and it contains something known as drive. So if I go into well message.drive, you'll see that the drive command actually has a steering angle velocity, speed, acceleration, and jerk. So that's the level of control that you can get with this type of message, which is an Ackermann drive stamped message. There are other command velocity where you can provide actual just linear velocity and a steering angle. Right. This is a little more detailed because it's running a car-like robot. So you want to be providing, at what velocity you want to steer and things of that nature. So it's a much nicer message to use. So here, all I'm doing is very simply providing a command to move forward with a speed of 3, stop, and then move backward. So as soon as I run this, see the robot starts moving forward, then it stops, and then moves backward slightly. And you can run this as many times as you want, and it's going to keep doing that same motion. All right, just to reset that. So I hope that clarifies just using publishers and subscribers. We talked a little bit about services. And if you're curious about that, we'd love to do another stream to talk more about how you can use actions and services. Nice.
Sounds good. What's next?
Right. So now that we've kind of just gotten data and sent out data, let's look at how you can create a stream of data, right? Because that's usually necessary. You're not going to do this once. You're not going to send command once and receive command once. So here, I'm going to showcase another workflow where I'm going to move the robot around. This time, I'm just going to teleoperate the robot. So first, let me set up the subscribers. This is what's going to actually give me my data. You'll also notice that on top of all my scripts, I always run ROS init to make sure that I'm connected. Just something that I do. It's not necessary for you to do. So we would be happy to share these scripts with you so you can try these out. The world is actually a separate world that I can give you a path to if you'd like to get that world, or we can package it as a part of the scripts to provide it to you. So I'm going to actually launch another node right now. So this is a standard node that comes with a lot of different projects. It's just a simple way of providing like keyboard commands to my environment. So let me keep this open. I'll scroll in and move this. Oh, I don't want to move my robot. I'll move this slightly forward and zoom in so you can kind of see what's happening. Right, so you can see if I were to put some commands, the robot would move forward. If I want, I can move it backward. So I have control via keyboard because I'm trying to show you how you can bring in a lot of data. Right, so here what we did is it's MATLAB, so you get to make really nice plots. I made a tile layout, and I've also added a runtime. I'm going to say for like 20 seconds, I want to keep bringing in data and displaying that data. So maybe the first thing you're going to start doing. So now you can see I have camera input, I have the LiDAR data on a polar plot, and I have some odometry data. As I start moving this robot, if I want, I can turn the robot. You can see immediately I'm getting camera data, I'm getting LiDAR information, and I have a good odometry plot. Right now, it might not be scaled to the right size, but as you move through this, it's going to scale.
Very cool. And you should be able to create something like this for any robot you're programming, right? Some
yes,
sort of
absolutely.
interface with all your sensors on it.
That's a really good point.
Yeah.
We will actually go to an app that we built to do just the same thing, where you can control the robot, you can maybe run a bunch of test profiles and see what the data came out. And here I'm just plotting the LiDAR data, but you can also plot the algorithm, maybe your sense and avoid algorithm. You can plot what your algorithm's deciding to do on top of the LiDAR data, so it gives you a lot of clarity on how your algorithm's working.
I think that's really useful, right? Because when you're programming robots, often the hardest thing is just trial and error and seeing what's going on, understanding what the data is telling you. So getting the graphics is going to be really useful.
Yeah, visualizing that data as your robot's doing the action is a really good way to have insight into maybe why your algorithm's doing something.
That's awesome.
And just one more cool feature I want to showcase here. This is a live script. I don't know if most of you have tried. Once you save this data, you can just scroll back and see this data again and again to confirm at each time point what your robot did, which is really neat. OK, so we've looked at bringing in data continuously. Let's maybe try to do something autonomous, right? Maybe we can. So I'm going to go ahead and reset this world again. And let me go and do something a little more. So this entire time, we've been working out of MATLAB, just live scripts. But you can do this from Simulink also. Because I'm already connected to the ROS network.
I'm not sure if there's anybody out there that haven't seen Simulink yet. But if you haven't, Simulink is this sort of like canvas environment for developing models for simulations. So that's why you see blocks. So it has blocks. It has signals. You connect them together. And you can actually generate things from this like code. So you can like generate C, C++ code from here.
Right.
So that's what this is that you're looking at here. It's like a complete development environment. Yeah.
Right. And as Jose said, here you don't actually write any script, but you use blocks and signal lines to run algorithms and move data from one block to the other. So here, similar to what I was doing so far, you can see I have some inputs. These are going to be my subscribers. I have some outputs. These are going to be my publishers. And in between, I have something for visualization, and I have something maybe to, just an algorithm. Here I'm using vector field histogram. What that's going to do is take the LiDAR data, the scan rangefinder data, and decide if the robot should continue moving forward. Maybe it should steer away from an obstacle that's right in front of it. So let's actually run this. I want to keep them side by side so you can see both of it. Give it a second to compile. Once it does, it's going to open up some viewers for you to take a look at. I'll actually go and follow this robot. Follow is a really nice way for you to keep the robot in frame while it's moving around. Do you want to maybe take a question while we wait for this to compile?
Sure, yeah. I think we have a question from the chat that says, can I load accurate DEM files from Google Earth to Gazebo? I'm actually not sure about that one, Ronal. Have you seen that before?
That's very interesting. I know for a fact that you can bring in STL files and represent your world from STL files. I haven't worked with DEM files, but if there's a conversion where you can take that DEM and build another representation that works with Gazebo, that's totally possible.
There's definitely a couple of ways to import things to Gazebo. URDF files. You can also include terrain data, I believe, now. On that particular format, I'm not so sure. But yeah, thanks for the question.
Yeah, I'd certainly like to look into it and see if I can find that. Oh, we have another one.
Yeah, can the files for this demo be downloaded?
Yeah. So as soon as we're done with this script, I'll try with this live stream, I'll try to compile all the files that you need for this demo and share it. Maybe we can put it in the description underneath our video, so you have access to go and download them.
So make sure to check the comments and the description after the recording goes live.
Precisely.
OK, that sounds
awesome.
good.
So good timing, because now we actually have this robot running. So I'm going to close these off. But what you can see is the robot's actually trying to move forward. That's all the command that I told the robot. Move forward and keep going forward as long as you can. If there's an obstacle in front of you, like maybe if I were to drop an obstacle right in front of it, saying, nope, you're not going to go forward anymore, the robot's going to decide, OK, maybe I need to steer left. Maybe I need to steer right. And I'm sorry about the performance. When running all this on my laptop, it does take a hit. You can see my real-time factor is at about 20. It's because I don't have a GPU on this currently. And if you notice that the frames are dropping, we actually do something to make your performance better. You can disable drop frames, and that's going to give you more frames. So you can see I'm getting camera information, I'm getting LiDAR information, and I can start. And here I used a single block. It's a block that ships with Robotic Systems Toolbox. It's called vector field histogram. So if you're building an obstacle avoidance algorithm, this is a great way to get started.
Right. I think it just goes to the ability of being able to grab things that other people have done, libraries, and reuse them, right? Not reinvent everything.
Right.
In this case, we're trying to just navigate without hitting anything.
Right.
It turns out that there's a library for that, right? And we just try to put it together in ROS.
Yeah, and the real cool thing about this is, you saw I was running the algorithm. I'm still running the algorithm. And any point, I can just hit reset. I can hit reset and make sure that, well, maybe I'll try it again. See, with a couple different parameters, I'll tune my LiDAR to have a different safety distance, a different range for actually looking at data. So I can continuously just go ahead and reset my scene, and then go into my model while running it as a simulation and change some of my parameters. And I can keep doing that till I get the
rapid
best.
iteration. Yeah, very useful.
I can tune it almost immediately.
That sounds great.
Awesome. So I hope that kind of gave you an idea of how you can work with Simulink, how you can work with MATLAB. Before I step forward, I want to kind of talk about anything that you build in MATLAB or Simulink. How do you now move this to your actual robot? So far, we've been looking at bringing in data into MATLAB, processing that data in MATLAB, and then providing commands to the robot. I would imagine most people at the end want to push everything that you've built directly onto your robot. So let's take a look at that. Right, so I'm going to minimize this for now, and I'm going to close off these windows. The first thing I want to talk about is from MATLAB, how do you deploy something directly onto your robot? So if you're working with MATLAB, the one thing that you have to do is build a function, because we want each of our nodes to be a continuous function that's running again and again. Out of Simulink, the entire model can be deployed. So when you work with MATLAB, make sure you write a function that you can then deploy. Now, I have some commands here that actually do the code generation for us, but I want to talk about this function a little so you get an idea of how do you write your MATLAB function. Now, if you generally write MATLAB functions, you probably have a return file and you have some input arguments. That doesn't apply here. In this case, you're going to have a publisher at the start or a subscriber at the start, which brings in some data. And then at the bottom, you're going to have a publisher, right? So that kind of closes your loop. Your function brings in some data from the subscriber and then pushes out data using the publisher. And you can have your algorithm right there. All right, so let me go ahead and use these commands. Now, of course, I'm doing the same thing that we did earlier, which was move the robot forward, move the robot backwards. A very simple example that I want to showcase here. So I'll copy these commands, and I'll go ahead and paste them. And I'll talk about these a little. So first, if you've worked with our coder tools, you have to have a configuration. What I'm saying is I want an executable out of it. And then I also say that the hardware that I want the executable to run is a ROS operating system. Now, there's another piece to this. Oh.
OK. And just while we're looking at that,
I had the wrong name here. That's it.
So if you're not familiar with what coder means, basically any algorithm that you develop in MATLAB, you create your MATLAB scripts or you use your Simulink files. You want to get it out of MATLAB so that you can share it or use it somewhere else. In this case, we're trying to put it in this RC card that we have over here in actual hardware. It just means that we, behind the scenes, take care of everything for you, that is writing C++ code, generating that, compiling it, and then move it onto wherever it is that the final destination for that code is.
Right. Right, exactly. So here, when I run this command, it's going to generate the files in my MATLAB current folder, and then I can move that over manually into my ROS environment and compile it using catcane or call compile if you're in ROS 1 or ROS 2. In Simulink, we do have a couple other features. I'll talk about that as we get to Simulink. So here, you can see that the code generation is running. You can see some folders being built here. If you're familiar with ROS, you know what a source folder is. It's where your nodes are going to lie. There's other folders that are built here, the message definition, that you don't have to worry about. The biggest thing that you want to move over is this file called command platform. Now, I've already moved this over to the environment. You can, because it's a virtual environment, you can technically just drag and drop. Just for my sanity's sake, when I bring in nodes that are not a part of the package, I actually put them in a separate Catkin folder. That just makes it easy. If I ruin something or if I mess up something, I can just get rid of what I built in. And you can see inside here, I have two actual nodes. One's command platform, one's sense and avoid. So command platform is the one we just generated here. I've already compiled this. I've already built it. So I can go into my terminal. I'm already in Catkin workspace, but I have to get out of that. So let's and move into the other Catkin.
That's your test.
Yeah.
Your test directory.
Yes.
Yeah.
So that's where I deploy most of my things. I do the same thing when I work with hardware too. I don't want to ruin my actual package drive, so I do it in here. And now I can do ROS run, which is slightly different from ROS launch that I was doing all this time. It's, if you're aware of bash scripts or shell scripts, it's a way of running multiple commands as a single script. When I do ROS run, I'm just executing one node. Whereas if you notice, when I launched AWS, Jose had mentioned, wow, there seems to be a lot of nodes here. That's because I built the launch file to launch all those nodes and set up the parameters as required. Here, I'm just launching one. So it's going to be command platform, and the node's also going to be named command platform. Whoop. Sorry about that. There's a lot of files in here.
There we go.
See, as soon as I run that, you can see the car behind me moved forward, stopped, moved backward. Right? So exactly what we had in MATLAB gets executed, and I'm running it on hardware. MATLAB's not running anymore. I'm actually running this as a node that's deployed on my hardware. I could run it again if I'd like. And I would do the same process if I wanted to move it to my actual hardware. So let me actually go ahead and turn on the hardware, because we'll be moving to that next.
Okay.
So very similar to this. Before I move to hardware, I want to quickly talk about what we would do in Simulink. So you saw I built a function in MATLAB, and that's how we're going to deploy our stuff onto our hardware. Now, in Simulink, there's a couple different ways you can do it. You want to go to the ROS tab, and you can go into deploy and just run build. If you do just build, what's going to happen is exactly like MATLAB, you're going to get a source folder that you can move over and compile. Now, I already did that earlier, so we can go ahead and look at my second sense and avoid. And that node is also going to be called sense and avoid. You can rename this if you'd like. You'll notice that this is going to do exactly what we saw a second ago. It's going to try to run forward till it gets to a wall or a dead end, and it's going to like turn and make sure that it doesn't hit anything. So it's going to continuously navigate around this environment so that it can freely move. This is actually what I do. Anytime I want to map a space, I just let the robot freely run around the environment so that I can map the environment and I don't have to like control it.
Sure.
Awesome. So that kind of showcases how you would how you deploy nodes from MATLAB or from Simulink.
OK, let's take a quick break. We're going to take a couple of questions. We're going to do sort of like a rapid fire. I'm going to try to answer a couple of them quickly, and then we'll move on to the hardware.
OK.
So I think one of the questions that came in said, can you explain the relationship between subscribers, services, publishers, etc.?
Sure.
We highly recommend that you actually go back and just quickly look at the ROS tutorials available. But basically, they all interact with the data and the topics that are in the ROS network for you to be able to connect different sensors and algorithm pieces together. Let's see. How do you do sensor fusion for ADAS using cameras, lidars, and sonars? That's a great question. This particular robot right here has all of these, right? It has a lidar, it has a camera, it has a 3D camera.
Right. No sonar, but it has an IMU.
Right. I think we have examples for that. just go to a product called the Sensor Fusion and Tracking Toolbox in our
Yeah.
documentation. There'll be like a full page of examples depending on the sensors you have and things like that. Okay, Ronald, do you want to take the next one? It's talking about how MATLAB is running on Windows,
Yeah.
while Gazebo is running on Linux. How
Right.
is that working right now, and how do they interface together?
Right. So when you're working with ROS, it doesn't really matter if you're running something in Windows or if you're running it in Linux. Now, ROS is natively ran on Linux, but there are ways to launch ROS even in Windows if you'd like. The interfacing between these, because it's a virtual machine, is a virtual network. Think about a router sitting between these that can communicate between them. Now, when I started, I did showcase that I set up my master URI and my ROS IP for each of my separate entities. And that's how they're able to understand where the master is, who's going to send messages to whom. I hope that clarifies it. But you can run it on Windows or Linux. There are some package managers. Chocolatey is one that I use that can open ROS in Windows. And of course, MATLAB, as you can see, can run ROS in Windows.
Cool. One more question. Any suitable projects for college students? So I'll tackle that real quick. If you're looking for robotics-specific projects, or in general, we have this program called the Excellence in Innovation GitHub repository from MathWorks, where we've put together a list of relevant topics, some of them related to robotics. There's some really cool projects there with like starting documentation that you can read through. And you can even get credit, and you can interface with MathWorks engineers to work on them as well. So check that out, Excellence in Innovation projects from MathWorks. Okay, I think we'll leave the questions there for now.
Right.
Ronald, why don't you tell us a little bit more about the hardware?
Let's go to the hardware. So as you can see, the hardware is sitting here. Generally, if it's a Linux system, an embedded platform, you can connect a display, a keyboard, a mouse to it, so you can work directly with it. But you can also, if it's on the same network, you can also just do an SSH protocol into the actual hardware. So that's what I'm doing. You can see here I SSH'd using the username and the IP that it's connected with. I have to enter the password, but now I'm in the actual robot. So first thing I want to do is move to my Catkin workspace, which in this I named as my race car workspace. I am going to source my devel, which is going to tell it where the ROS operating systems are. And then I can go ahead and run one of our pre-existing nodes that I had. So here I'm actually going to run a teleop node. So ROS launch, race car, which is the package, and teleop, which is the actual launch file. So as soon as I run this, you can see that it's going to list out a lot of different nodes that are a part of it.
And just to clarify, this is now making the car active, right? The real one that we have here in studio.
Right.
Okay.
Let me just confirm that the IPs are set correctly, because it didn't seem to want to launch. So let's see what my IP is. Oh, that's why. OK, so you can see that for hardware, I have to have a separate IP. So I'm going to go ahead and export that. Ooh. 20.
And if you've worked with robots before, you know
39.
that the IP address is something that keeps coming up. When we had the virtual machine had an IP address. Now that we're changing to the robot, there will be a different one. It's all networking sort of concepts. And
Right.
Yeah, if you have any more questions, yeah, feel free to follow any other links that we post in the description and comments later. We'll take a question. It says, can we extract sensor data, radar or LiDAR, from a MATLAB simulator? Oh, that's a great question. So for instance, this Gazebo simulator, we already showed you how to extract LiDAR data. There's other MATLAB available simulators where you can actually do high fidelity sensor modeling. It basically just means that you can tune all the parameters in there and then also like create what is called synthetic data. So you can get LiDAR scans simulated and then obtain that for further testing.
Ooh, I think I'm almost there. You want to take one more question?
Yeah, let me see. There says, can you use MATLAB and Gazebo from the same virtual machine? Yes, you certainly can. For instance, this virtual machine that we're using is running Linux. You could certainly install a Linux version of MATLAB in it. In this particular case, it might be a little bit slow, but depending on the computer and the setup for your virtual machine, you can definitely do it.
Right, if you have a powerful enough processor, and I would recommend a GPU, because the virtual machine, you're running Gazebo, which takes a lot of graphical input. So having a GPU is going to make things a lot faster, for sure. Another way you could work with this is you could have Gazebo running on a separate machine and MATLAB running on a separate machine. That if you have two PCs that you can use, that would provide more resources.
That would be my recommendation,
I
actually, yeah, because Gazebo can actually run pretty quick, and it'll give you like sort of real-time performance if you're interested in that. So if you have the ability, try setting up sort of your environment in a separate computer and then connecting those over a network.
Okay. Exactly. So now you can see that once I entered the right ROS IP, unfortunately I got the wrong one first, I have all my nodes that are actually started showing up. It's the same set of nodes that we saw already. It does say that the joystick is not found. That's because I haven't connected one to it. But you can also see like my RGB, my LiDAR, and my odometry are getting published. So let's come back to MATLAB. Now that the hardware is running, let's come back to MATLAB and see how we can connect to this. Let me make sure I have the right ROS IP set up. All right. So again, I'm going to run ROS in it, so I know that I've connected to it. You can see the list of nodes, very similar to what we saw in the package. And this is why I say start with the simulation environment. You're going to get the same nodes. You can almost get the same performance in your simulation environment before you come to hardware. Of course, eventually when you come to hardware, there's some knobs, some tuning that you would have to work with. But you're almost 80% of the way. And you're not running to grab the hardware every time. All right, so you've already seen most of this. Similar commands, I just want to show you that your subscribers, your info, all your ROS commands are going to work just the same. This is a laser scan. So it's actually going to give me what this LiDAR is visualizing. It's not a lot of information. If you look at it, it's put it all together. But let me see if I can zoom in. I'll show it to you live so you can see us actually moving.
That's us in the studio, but you obviously can't tell who we are from the dots.
And then, of course, I can also send some actuation commands to it. So,
whoa.
What it did was the same thing, right? It moved forward a couple, and then it moved backward a little. I can send that a couple times. This way, you can also make sure that you're getting the right speed, and you can tune it to, not have a lot of jerky motion. Now, if you notice, this specific topic lets you control acceleration and jerk. So that's important, especially when you're mapping. You don't want to take off because then your LiDAR shoots up and then comes down. Your map is going to be a little all over the place. OK, let's go back to the sense and avoid and see, now that we're connected to the robot, if we can run this again and see what the robot sees. It is going to be a little jerky because we're so close to it. It's always going to want to move that way. Give it a second to initialize. But once it does, you will see actual image frames.
Okay.
Oh, I might have disabled the output command. Sorry, give me a second. So this is another thing I want to showcase. Once you're already connected to the network, when you go to our subscriber block, it gives you a list of all the available topics. So I'm going to go and select RGB image raw color. And scans good for me. I'm going to keep that. When I go into my actual output topic, I'm going to go and select teleop. So those are some changes just because of how the topic was named in my simulation versus the hardware. Now I can run this again once they open up. Whoa. If we move further away or get closer, it's going to want to actually move in that direction. Not sure why I can't get RGB data from it yet. But you can see as I move away, my LiDAR data actually changes. This is a very small environment for this to be sitting in, so maybe I'll, while it's running, go ahead and change some parameters to make it a little happier being in this confined space. Right, so now it's moving that way. If I were to keep this, it's gonna, sorry, it's gonna jerk a little. If I get a little further away. Now it's clear to move forward. If I come close to this side, it's gonna turn away from me. If I move away, it's gonna go forward. And if I come through this side, it's gonna try to go that way. So again, the same sense and avoid algorithm that we tried on our, I'm gonna stop this so it doesn't fall off the same sense and avoid algorithm that we ran in our simulation, we can test it. Of course, I don't have the room to run it around here. That's why I decided this would be a good way to showcase it. But that's the first steps, right? We got data. We sent messages to the actual robot. We did something more where we brought in data, analyzed the data, and then decided what action we want to take. So that kind of covers all the different pieces from bringing in data and then finally deploying an algorithm onto the robot itself.
And I don't know if you guys noticed, but just to highlight, the script that Ronal used was exactly the same script that he used for both the simulation and the car. So all he did was literally change the IP address and then contacted a different network.
Right.
And then he literally ran the same algorithm in the robot, which is super useful for prototyping. And that was also the case for the Simulink model, right?
Right. I didn't change anything. I had to change a topic just because the topic's named differently, but my algorithm and my control parameters all stayed exactly the same. So you can do all the work ahead in simulation and then just deploy it to your hardware and see how that works. And you have to make no changes other than an IP address.
Yeah, that's really cool.
Awesome. So with that, I kind of want to move on to one more thing that I want to showcase here. Now, the environment that I launched here was an AWS environment. For most of you, it's possible that this is not the environment you want to work with, and you have a custom area that you want to actually work around. So what I want to showcase is an open source package. It's called Map to Gazebo. It's a really nice package. What it takes is an occupancy map, a binary occupancy map, and it generates a world for you. So here, what you see is, and this is what I used. This is my level of the office. So this is Apple Hill, where we have MathWorks headquarters. I took the floor plan of Apple Hill. I converted that using a single function in MATLAB, and I got an occupancy map. And from that map, I was able to generate this scene.
That's really cool, yeah.
And this is in Gazebo. It has walls. It knows all the different spaces, what the sizes are. And of course, you can scale it if you want. If maybe your floor plan is not precise, you can scale it to be the right size. One thing I would recommend, if you're not going to work with the entire floor, maybe don't bring all of it. The more data you have in your Gazebo world, it's going to take more resources. So if you're only working with one corner of this environment, maybe just bring that in, and that's your more important piece. So let me show you how that looks in Gazebo here. This is our AH2 environment. So you can do almost everything that I showcased just a second ago in this environment. And this is kind of where I did all my prototyping, and I'll show you what we got to. So here you can see this is my Apple Hill 2 floor plan that I've converted to an environment. You can also see that I already have the robot initialized in this environment. This is my office. It's very common for me to start right outside my office, so that's where I've initialized the robot. And now we can do everything that we did in this environment. So for the next pieces, I'm going to quickly go through some slides to kind of walk over what you can do. This is not pertaining to ROS, but if you're building autonomous algorithms and deploying them, this is most likely what you're going to be working with. So first is generating a map of the environment. So you can see in the right here, I'm moving the robot through that AH2 environment. I'm getting a laser scan at every rate that I want. I'm running this robot through, and using our internal SLAM algorithm, I'm able to build a map. And you can see the generated map up there. And this is what I did. I did this for the entire section that I want to navigate. So then once I have a map, I can go into the next piece, which is creating a plan. Now, most planners require an occupancy map as a state validator. And so here you can see I took a section of where my office is and where my coworker's office is. And then I went through different plans to see like how long does it take to plan, how nice is the overall plan that I get, do I have to do some smoothing to the plan so that the robot can actually maneuver this environment. Now I already talked about this, but I want to talk about one specific thing in Simulink. So we looked at simulation, right, where you have Simulink running, you have an environment like the H2, and you're looking at what your robot does in that environment. I want to talk about, so this is just in simulation. It's actually working in Simulink. I want to talk about external mode. This is actually a really nice feature that Simulink provides that what it does is you get Simulink as a GUI where you can see all your data. You can see what data is coming in, what data is going out. But you actually generate code and deploy it to your hardware. So before you go to the final stage, which is taking that model and running it on your hardware, external mode lets you run your model within Simulink or use Simulink as a GUI to give you data, a debug screen, but it's actually running on the hardware. So that's really nice because you can run it on hardware, but at the same time look in Simulink what your data is. And you can even tune parameters on the fly because everything in external mode, everything that's a control parameter becomes a ROS parameter, so you can change it as required.
And I think you got a little taste of that when Ronal ran that simulation. If you notice that he was changing parameters, he did it on the fly, the robot reacted with him. That's the type of debugging that you'd be able to do with it if you go back on the recording and look at it.
Right, and that's always going to be the case. Not almost all simulations are going to be slightly different than the actual hardware, so you're going to have to do some debugging on the hardware itself. And then this is finally deployment. We already talked about it, so I'm not going to spend any time on it. I do want to touch on one piece before we close off for today. Not everyone requires a really high fidelity simulator. This is actually showcasing 3 test environments that we use to build this. The first one's a cuboid environment. It's really easy to build. It's all based out of MATLAB itself, and you can still do most of what you want in that environment. It still gives you LiDAR, IMU, GPS, all of that's available in there. Now, if you want to go to a slightly higher fidelity, maybe you want some platform dynamics, you want a camera, then Gazebo is a good place to start with. But as Jose had mentioned, sometimes setting up a Gazebo environment is a little tricky and it could take time. So cuboid's probably a good way to start. And then finally, actually running it on hardware.
Cool.
I did want to mention a couple more things. Because you're working with MATLAB, you get access to a lot more functionality. So here you can see on top, I'm taking my LiDAR scan, and I'm actually plotting it on top of my map. This is using Monte Carlo localization. So I'm using that LiDAR scan to relocalize my robot as it goes through the environment. Pre-built, ready for you to use if you'd like. And then this is the final run where I have, oh, sorry about that. This is the final run where I have, it's running in external mode. I'm making sure my localization is working the way it's supposed to. I'm making sure that my sensor data is coming in exactly how I need it to. And that makes it really easy to debug anything that happens. If I see that the robot's turning too much to the right or left, I can look at the LiDAR data to see why. So you can notice this robot tends to bounce around in the center when it travels through there. That's because it gets LiDAR data from walls, or sometimes it's just a glass. And it's trying to stay in the center. So when a glass comes, it decides, oh, I need to move closer to this wall because it's a glass. Right, that's really all we had for you today. We can certainly go up into questions. I can leave this slide open, which is just a conclusion. Maybe we can take a couple questions before we close off.
Yeah, I think that was a lot of great information, and this slide sums it up. I'll do a quick summary for everybody out there. We talked about ROS. We talked about robots that are powered by ROS and how to interact with them from MATLAB. You can do it through scripts. You can interact with subscribers, publishers, with all of the sensors and actuators in your robots. Then you can also move on to Simulink. You can do the same in this modeling environment where you can actually generate your nodes, put them in your robot permanently if that's what you're looking for, and then test and debug and try things that way. Yeah, I think that about covers it. So please put your questions in the chat. We're going to try to go through a couple of those right now.
Awesome. So I guess we have one that asks, would you recommend to only work on Linux, or is the Windows version of ROS2 just as good? I think when you're starting out, the Windows version is just fine. Eventually, when you're going to deploy this onto a platform, that might most likely be a Linux platform. So in that case, I would recommend also using a Linux environment, because your final state is going to be in a Linux environment. The Windows version is a good way to start off if you're not aware of Linux and you don't want to deal with some of the Linux commands. But I would still recommend moving to Linux. And ROS works natively in Linux. A lot of packages that you get compiled really well in Linux.
And a lot of the micro or mini computers that you normally use for this type of applications, they generally are much happier with just Linux environments.
Right.
So, OK, and we have another question. What other simulators can be used? Just straight off the bat, if your simulator is able to interact with ROS, then all of the ones that can interact with the robot operating system topics, subscribers, and all of those will be supported. And we invite you to visit our documentation as well. You can use with MATLAB Unreal. We have some dedicated high-fidelity simulators, like Ronald said, the cuboid environment.
Right.
So there's certainly a couple of different simulators that you could use.
Precisely.
I think that's about it for us. We hope that you enjoyed this live stream. There's a lot of content related to ROS and robotics. Thank you so much for attending. Feel free to leave your comments and questions in the chat and in the comment section below.
Right, just one more thing. Do come back and look at the description, because we'll be putting the files that we used for the demo today there for you to download and try.
Thank you very much, everybody. We're going to go ahead and sign out.
Thank you so much.